Hi friends, today let us understand some basics of limits. Okay, to start with, let us take a small graph. What is the graph? The graph of y equal to x plus 1. This one. Y equal to x plus 1 is a straight line. Right? When x equal to 0, y is 1. When x is 1, y is 2. Whatever. Okay, so this is a straight line graph. Let us take a small variation of this in this form. X square minus 1 by x minus 1. This is also equal to x minus 1 into x plus 1 by x minus 1. Right. If we cancel x minus 1 x minus 1, we'll get x plus 1. So is this equal to this? That is the question. Okay, this is almost identical, right? This is not exactly equal. Why? There's a small problem here. When x is 1, this graph is not defined. Right, when x is 1, this graph is not defined because the denominator is 0. But this graph is always defined. This graph, the domain is R. From any x minus infinity to plus infinity, any x, y is defined. But here, this is almost equal to this, except for this one point, which is when x equal to 1. Okay, when x is equal to 1, this graph we don't know. What exactly is this value? Okay, but we have a feeling that if someone has to fill this graph, this is called a hole. This is a hole. We call this a hole because we don't know what is this value. But this graph and this graph are very much identical. If someone wants us to fill this hole, then we'll fill this with this point 2. Right? We'll fill this graph with this point 2. Right? So now when x equal to 1, when x is tending towards 1, f of x, we call this f of x is tending towards 2. Okay. When x is tending towards 1, f of x is tending towards 2, but f of x is never 2 because when x is 1, it is not defined. Okay. So we call this as limit. Okay. Limit means the function is coming very, very close to 2, but probably it cannot take 2. As close as you want. Right. The function will come as close as you want. For example, if you want 1.9999, you will get. When x is 0.9999 something, 0.999 something, 0.999 plus 1 is 1.99, you will get. Whatever number that you want, close to 2, you will get. Exactly, but getting exact 2 is actually not possible. Right. So that's why we call 2 as limit of this function. Limit of this function when x is approaching 1. Okay, so f of 1 is not defined. Please note, limit of this function need not be f of 1 because f of 1 is not defined. Here, limit of this function when x approaches 1 is equal to f of 1 in this graph. Right. In this graph, we say x is the limit of this function when x approaches 1 is actually 2. Right. Let us take another example. Okay. So let us take these three cases. We are defining this function x square minus 1 by x minus 1. Obviously, at x equal to 1, there is a hole. Okay. Here in this function g of x, we are trying to fix this hole by defining some other number. When x equal to 1, we are defining this as 1, not 2. Here, h of x is x plus 1. Here, if these three cases if you take, here f of 1 is not defined. Right. But limit x tends to 1, we call it x tends to 1, f of x is 2. Okay. In this case also, limit x tends to 1, f of x is 2. Okay. So we can make this function as close to 2 as possible. Right. So this is called limit. In this case also, limit x tends to 1, f of x is actually equal to 2. But here f of 1 is 2. Here f of 1 is 1 because the function, the definition is given as when, no, sorry, this is not f, this is g. This is g. This is h. Right? This is h. Okay. G of 1 is 1. Here, f of 1 not defined. Okay. Please note the difference between first and second one. Here, f of x is as close to 2 as possible for all the x's, for all the x which are close to 1. Okay, which are close to 1, whatever the x's in this range. For all of these values, the y's are very close to 2. Okay, so they look like they are approaching 2. But here, if it, here also, they are approaching 2. So that's why the limit is 2. It cannot be 1. Because the x is very close to this point 1. The value of f of x is here. It is not here. Right. If it was close to 1, we would have called it as the limit as 1. It doesn't matter what is the value of the function. The value of limit is very close to f of x, very close to x. How is f of x behaving? That is the limit. Not exactly the function value of the function at x. Okay. At 1, what is the limit? Very close to 1. What is the value of function that is happening? Okay, very close to 1, it is approaching 2 from both the sides. Right, but here also very close to 1, it is approaching 2 on both the sides. That's why here also limit is 2. Here f of 1 is 1, but it doesn't matter. Okay, let us take few more examples. Okay, in this case, f of 1 is 1, sorry, f of 0 is 1. So y is 0 when x less than 0, and y is 1 when x is greater than or equal to 0. So here does limit exist at x equal to 0? Limit at x tends to 0. Okay, so here there is no limit. Why? When x tends to 0, very close to 0, the value of the function should approach a common number. But here in this case it is approaching 1. In this case it is approaching 0. So so there is no common number here. When they both are approaching a common number, right? Some common L, that we call it as limit. But in this case, when we are taking very close to 0, x is moving very close to 0. From this side, it is approaching 1. From the left side, it is approaching 0. So limit does not exist. So there is no limit here. In this case also, here if you are approaching from the right side, it is trending as plus infinity. But you are approaching from the left side, very close to 0. X is very close to 0. What is the value of this function? Here it is minus infinity. So there is no common point to which both sides are approaching when x equal to 0. For example, if we take some point like this, here limit exists because from the left side, from the right side, both values, let's say this x is some 3. Okay. So between this and this range, both sides, the value of the function is approaching to a common point. So at this point, limit exists. At this point, limit exists. At this point, limit exists. At this point, this point, all these points, limit exists. But exactly at 0, it doesn't exist because one side looks like it is approaching some value, another side it is approaching some other value. Both values are not common. Right. Let us take this another function. This is y equal to 0 when x less than or equal to 0, and sine 1 by x when x is greater than 0. Please note sine 1 by x. Right. 1 by x, when x is tending to 0, what will happen to 1 by x? 1 by x tends to infinity. Okay. 1 by x tends to infinity, that will, there is lot of fluctuation. So for example, sine, sine, uh, sine 200, sine 201, sine 202, whatever, or sine 5000, whatever. So the number fluctuates a lot. Sine always remains between 1 and minus 1. But if you draw this graph, as it approaches 0, if x approaches 0, it will fluctuate a lot. It will fluctuate a lot. And there is no common number towards which this function approaches. From the left side, if you see, it is approaching 0. From the right side, you cannot say whether it is approaching 1, approaching minus 1, approaching 0.5, whatever. We cannot clearly say. So it is not approaching a common number. If it was approaching 0, then we can say the limit is 0. Limit x tends to 0 is 0. But in this case, it is not approaching 0. It is fluctuating a lot. Okay, in this case, it is going up. One is going up, another is going in another direction. In this case, we don't know what exactly it is. As it comes closer and closer, the fluctuation increases a lot. So we never know to which point it is approaching. So here also limit is not possible. In all the three cases, limit is not possible. So broadly what we are saying, very informal definition. The informal definition is, um, if there is a limit, the function should approach f of x should approach this limit as x approaches x0. X0 is the point at which we are concerned about the limit. Okay, for example, if this point 0 is the point, if there is a limit, then from the left side and from the left right side, the function should approach that value. Very broad informal definition. We'll get to precise definition later on. Okay. So now once we define limits, okay. So different functions have limits. There are some broad rules like some rule, difference rule, etc. etc. Let's say there are two functions. Limit x tends to c. Please note x tends to c in both the cases. There are two functions. First function the limit is L. Second function the limit is M. Then if you are adding the functions, we'll add the limits also. When subtracting the function, here also we can do n minus m, right? So constant, multiple, product rule, whatever, right? Basically what we are saying, if there are two functions and both have a limit at x equal x when x tends to c, right? Then we can add both the functions and their limit is also equal to the sum of the limits. Their difference of limit of differences is equal to difference of limits. If one of this function is multiplied a constant, and if we try to find the limit of constant into function, it is equal to constant into limit. Similarly, product of functions will be, if we try to find the limit of product of functions, it is actually equal to product of limits. Similarly, for division also, for power also, for under root also. Please note, while under root, whatever limit that we are talking about, that should be greater than 0 if the root is a um, even number. If it is an odd number, that should be fine. Okay. Now, let us take some basic examples using this limit rules. Okay. For example, if we are given this function, here basically there are three parts, x cube, 4x squared, minus 3. Basically, this is like three functions. We have just decided when there are multiple functions, the limit of the sum of the functions is equal to individual limits of the function, sum of individual limits of the functions. That's what we will do. So this becomes limit x tends to c x cube, limit x tends to c 4x squared, limit x tends to c 3. Okay, the sum of limits of individual parts. Okay, so what will this become? C cube plus 4c squared minus 3. Basically, we are substituting c in all the three places. Similarly, let's take this one. Okay, so this is what? This is division rule. What is the division rule? Division rule is if there are two functions, ratio of two functions, then we can take it as limit x tends to c f of x by limit x tends to c g of x. Basically, limit fractions. Right, we can do this. That's why here also this limit, let's say this is f of x, this is g of x, we are using the quotient rule. So we can take limit in the numerator also, denominator also. This again we are using the sum rule. Sum rule is this one. Okay, limit of sum of functions is sum of limits of functions, right? So here also we can use the rule. So that's why limit goes inside. So this becomes c power 4 plus c squared minus c by c squared plus 5. Okay. Okay. So here we are using the basic formula, product rule or power rule or division rule and all. Similarly, the third one. Third one, if you try to see, okay, there is a square root here. Okay. What is, we have used this, we know this. What is the rule? Limit x tends to c is square root of f of x should be equal to square root of limit x tends to c f of x. Right. Square root of limit x tends to c f of x. Okay, we can take the limit inside. Basically, what this means is very basic algebraic manipulations. Now, here again, this is a function f of x, g of x. So, difference of two functions. So, that's why we can take limit with both of them. Right. So, we'll break this as limit x tends to minus 2, 4x square minus limit x tends to minus 2, 3. And here we can directly substitute. Okay, x tends to minus 2 means we can directly substitute here. So 4 into minus 2 whole square minus 3. So this becomes root 30. Basically, what we are doing is we are just substituting when x tends to c, we are just substituting uh, in this expression, x in this expression, value of this x in this expression, right? Now let's take one more example. X square plus x minus 2 by x square minus x. X tends to 1. But in this case, we cannot directly substitute, because if we substitute, this becomes denominator becomes 0. So we use a method called uh, breaking this into factors. Okay. So we can see x square plus x minus 2, we can write it as x minus 1 into x plus 2. So denominator also x into x minus 1 we can do. So this x minus 1, this x minus 1 we can cancel as long as x is not equal to 1. Otherwise 0 by 0 we cannot cancel, right? As long as an x is not equal to 1, this fraction becomes x plus 2 by x. Okay. So now limit x tends to 1. What we are saying, this means we know as long as x is tending towards 1 from the left side or the right side, except at 1, the value of the function is this, right? When it is tending from the left side or when it is tending from the right side, the value of the function is this, right? So now what we can say, if you substitute x equal to 1 in here, 1 plus 2 by 1 plus 2 by 1, which is equal to 3, this is the limit. So this function, this f of 1, let's say if this is the function, f of 1 is not defined. Okay, is not defined. Basically, this is equivalent to our first problem. First problem. Here also, f of 1 is not defined. But we simplified this to this form, where f of 1 is defined. So whatever is the hole, we are trying to fill that hole with a realistic number. That number is this, right? Now, here also, we are trying to fill that hole. At x equal to 1, this function is not defined. But what is the value of that hole? If you have to fill, the value of the hole is actually equal to 3. Right, guys? If you look at the graph of this function, x plus 2 by x is this entire graph. Okay, this graph. When x equal to 0, left, as we approach from the left side, it will become minus infinity. From the right side, it will become plus infinity, whatever. Okay, but this graph is the graph where this one point is missing. This one point is missing. When x equal to 1, this point is missing. But this graph, x plus 2 by 2, which is identical to this graph, except for the point when x equal to 1. That is this graph. Okay, so in this graph, when x equal to 1, y is 3. Y is 3 in the simplified graph, right? In the simplified graph. So now if you have to fill this hole, we'll fill this with this 3. So that is the limit, right? So basically what we are trying to do some algebraic manipulations to simplify this graph to get an identical graph which might be defined, which has a value at x equal to 1. We are trying to find an identical graph, identical function. We are just trying to simplify this function, the function which is identical to this on all points except when x equal to 1. That is this function. Now this function, how does it behave when x equal to 1? It will give a value of 3. So we are saying that when limit x tends to 1, though we don't know what is the value of this function is approaching this value 3. This function is approaching this value 3 when you are moving from the left side or from the right side, because the identical function will take the value of 3. Right, guys? So here, this is the graph, right? X square plus x minus 2. Here, there is a hole here. Here, that 1, 3 is there. So we'll take this point and call limit here as 3. Limit x tends to 1 for this function, we'll call it as 3. Right, guys? Let us take another function. Under root x square plus 100 by x square, sorry, minus 10 by x square. Here also we cannot directly substitute x equal to 0 here. So here we'll do some kind of rationalization, or we'll use the conjugate of this and multiply with both numerator and denominator. The goal is actually to eliminate this x square in the denominator, to eliminate the 0 in the denominator. So we'll do this multiplication, this by this, both is equal to 1. We are just rationalizing the numerator by multiplying with the conjugate. Okay, so this is in the form of a minus b into a plus b, which becomes a square minus b square, that is x square plus 100 minus 10 square, which is again 100. So x square plus 100 minus 100, right, by x square into um, x square plus 100 minus 100 by x square into under root of x square plus 100 plus 10, right? This 100 will get cancelled, this x square will get cancelled, we will be left with 1 by under root x square plus 100 plus 10, right? We will be left with this. Now now we can directly substitute x equal to 0 here. Basically what we are trying to say, this graph is actually identical to this graph, except one, probably when x equal to 0. For all other purposes, this graph is identical to this graph. Now this graph, when x equal to 0, it will give us a value of 1 by 20, right? 0 plus 100, which is root 100, which is again 10, 10 plus 10, 20, 1 by 20, which is equal to 0.05. So we call this limit of this function when x tends to 0 as 0.05. Okay, because we have created some identical graph. Okay, some identical graph whose value is 0.05. Right, guys? Now let us understand some more questions. Suppose that a function is defined on all real values of x except at x equal to x0. Okay, so there is a function. It is defined on all real values except at x equal to 0. Okay, can anything be said about the existence of limit at x equal to, as x tends to x0, f of x? Okay, so firstly, for limit to exist, it's not necessary that the function is defined at all values except x equal to x0. So for example, if you define a function like this is x0, or we have defined multiple functions, right? Like this, 1 by x. 1 by x, when x equal to 0, the function is not defined, but for whatever other value, the function is defined. Can we say there's limit exists at x equal to 0? No, we cannot say, because on one side it is